And we've got most everybody online now. Seems like the recording is starting. And we've got most everybody online now. I have to mute the audio on there, so we get it with like a 30-second delay on the YouTube, huh? All right. And let me make sure that I am connected with, I get the microphone, I got my headphones. Okay. Outstanding. Let me turn the video on. Great. Welcome everybody to our first Wednesday lecture. It's very exciting for me to be talking to you on a Wednesday, especially while Emily is talking with her teacher on the Wednesday. We're going to do a couple things today. I want to spend some time talking about chips and chip formation in machining. I'll stop that screen share. All right, so we want to talk about chips and chip formation in machining. And we want to talk about how that will impact us and how we can understand how to progress from one force system to another. There's really three force systems that are interesting to us when we're looking at the cutting forces here, and we want to learn how to move from one force system to the other. So just very quickly, what does power equal?
Work times distance.
Power equals work times distance. Is that the right units?
Isn't it the rate of work over time?
Yeah, isn't it work over time?
That's it, yeah.
Yeah. Okay, good. I hate it when I ask a question like that and I get an answer and I don't think it's the right answer, but oh, what if I remember wrong? Ooh. And then if I say it wrong and then they believe me, I could screw you up as engineers for your entirety if I remember something wrong, huh? So if I make a mistake, please tell me, because it has, well, one time I thought I was mistaken, but it turns out I was wrong. All right, I'll get to that in a second. So power equals work over time is the rate at which work is done. What else does power equal?
Force times velocity.
Power also equals force times velocity. Okay. And how are we measuring power? How can we measure power? In CNC machining, that's sort of our example thing here. If we're doing CNC machining and we want to measure power, how can we measure power? I could start picking people. I should pick people that don't have their camera turned on. Matthew, if I'm doing CNC machining and I want to measure the power, how do I do it?
There's more than one Matthew.
Oh, well, the Matthew that I'm thinking of is Cope something. It doesn't show your whole last name. Matthew Cope something.
It's
Cope.
It's Copeland.
Copeland. Yeah, I got the Copela. I could have guessed Copeland, I guess. But it could have been Copelala. Matthew. If you're doing CNC machining, I'm sorry, I'm laughing at my own jokes. If you guys don't want to laugh, it's okay. But if you're doing CNC machining and you want to measure power, what could you do?
You could use the equation we found yesterday, or you could look at the spindle load on the machine itself.
Right. So you could measure the amperage and the voltage going to the motor that's causing the cut to happen. So you could look at that spindle load, and you don't have to just use the meter on the machine. You could get much more sophisticated measurement tools and data acquisition systems to accurately know the dynamic loads that are happening on there. Because what you see on the needle on the machine is pretty averaged over time, and it's intended to just give you a guide of how much of this machine's capacity are you using. But you could very accurately measure those things. Or you could measure the cutting force and the velocity or the surface speed, and you could calculate the power based on that. So those are two pretty easy ways that we could measure power if we want to with our CNC machining. Okay, so why did we care again about measuring power? I remember we cared about measuring power, but I don't remember why. So why would we want to measure the power when we were cutting? Pick on somebody else. Philip.
It can measure the cutting speed.
You said something about cutting speed. So we could know the cutting speed by measuring it or by assuming it is what we programmed. But to want to know power, so somebody said by measuring power output, we could determine spindle load. So we could measure forces to get spindle load back. It definitely can have an impact on cost. If we were going to set up an experiment where we were going to measure the power, what would our possible rationale be? Why would we measure it instead of estimate it, for example? Philip Lund, why would we measure it instead of estimate it? So you get a short last name and then it fits on the screen. There's some pretty long last names that fit on the screen too. How about Tyler? Oh, go ahead.
I was going to say I'd probably want to measure it rather than estimate it because, for one, you'd be able to do so with things like a spindle load, if I recall.
Okay, so one reason we might want to do it is if we want to optimize our ability to make the cut, and we know how much power. So this is not optimize as in reduce the amount of power that we use in total. This is optimize as in get the chips in the bucket as fast as possible and make the parts as fast as possible. And so if we can monitor the power, we can know how much power we have available. We could maximize our parameters. So our cutting parameters, those the PVs, the things we get to choose, we could maximize those to make the parts as fast as possible. If power was our limiting factor with our machine tool. So that would be one reason we might want to do that. Now, if power equals force times velocity, we might want to estimate the power to get some idea of what the forces are going to be. Does that make sense? I'm going to just assume you all shouted yes, but you had your mics muted. Yes. So of course it makes sense that we might want to get a feeling for what the cutting forces are going to be. Now, why would we care what the cutting forces are going to be a priori? So before we start the operation, why do we care what the cutting force is going to be?
Cutting forces, if they're too high, then the tool might break.
So if the cutting force is too high, the tool might break. That happens. It happens because the cutting force is too high. Why else might we care what the cutting force is going to be? Why else do we care what the cutting force is? This is the first time I've ever had a classroom that was in the kitchen, which means if I want a drink of water, I can walk over to the sink and get a drink of water. But why else might we care what the force is? So we care about breaking the tools. What else do we care about?
different cutting forces will cause different surface finishes?
So a change in cutting force might cause the surface finish to change. That's probably true. I don't know if anybody's ever studied the relationship of cutting force to surface finish, but intuitively I believe that that's true. Why else might we care about what the force is?
Might determine how deep we can make a cut.
So the deeper we make, so if I make a cut deeper, so if I increase my depth of cut, is the force going to go up or down?
Up.
If I increase my depth of cut, the force goes up every time if I don't change any other factors, right? What else would make the force go up every time if I don't change any other factors?
Speed.
Depending on the units you use for speed, either yes or no. But okay. What else makes the force go up no matter what I do?
Tool size.
You mean if the tool gets bigger, the force goes up? The person who said tool size, does that mean so if the tool gets bigger, if you get a bigger tool, then you can withstand higher forces. Besides breaking the tool though, what happens when the force goes up?
The piece you're trying to machine can start to bend.
All right, so the piece we are machining will deflect no matter what the force is. If the force goes up, it will bend more. Right, so there's always some amount of deflection. Both actually it's kind of amazing because these carbide end mills, you'd think that they're pretty rigid, but as the end mill is moving through the workpiece material, there's a force on it pushing sideways, and it bends, and it actually causes the spindle to deflect, and it causes everything to bend a little bit. So the edge of the end mill isn't really where we think it is at any time. Although if the forces are very low, then we probably can't measure the amount that it deflected. And so that's a case where high forces can cause surface finish to change, because what happens is it causes the tool to deflect, and then eventually the tool can't deflect anymore because it's building up stress in the tool itself, and it pushes back, and the tool starts to spring back and forth, and it vibrates and it makes chatter. And so that's a case where increasing cutting force might cause the surface finish to be impacted. Now, it's interesting because often we get that chatter situation when it's not that we've got too high of a cutting force, but sometimes it's when we've got too low of a cutting force. Are you done with your Zoom? You got kicked out. Were you being nasty?
No, I think I accidentally clicked something.
You accidentally clicked something? You want some help? I'll be right back. You might not be kicked out. Okay, I think you're just gonna have to wait till it connects. She accidentally exited. Oops, it's connecting. All right, so chatter causes that. Often increasing the cutting force will make chatter go away, so it's kind of counterintuitive. And if you've got your hand sort of on the feed rate knob, and your tendency is often to back off on the feed rate, but increasing the feed rate is often more likely to make the chatter go away. So, but the thing that nobody said that I was trying to get you to say, and finally I'll just say it, when the force goes up, besides bending the workpiece and bending the tool, we have to worry about whether or not the workpiece is going to stay in the fixture. And so we're going to talk a lot about fixturing and stuff, fixture design tomorrow, and it's going to be based on the stuff we talk about in forces today. So forces are important to us, both because too much force will break the tool, but often we have to limit the force, not because of the strength of the tool or even the strength of the material. We have to limit the force to make sure that the material stays in the fixture that we're using to cut the workpiece with. All right, so let's jump into, I got some slides here I want to go through. So let me see if I can find them again. So yesterday we did this energy and power stuff. Today we're doing power and forces. And let me present. And let me share the screen. Where did my little Zoom go? Where could it be? Zoom, menu bar, where are you? Ooh. Just a moment. Oh, there, I found Zoom. He was hiding under another window. Nope, that's not Zoom. Now I have found Zoom, hiding under another window. And now I can share my screen. And you should see, I'll share the sound too, just in case there's any fun sound. All right, power forces and chip formation. Did you get back in? You want to try again? Let's try one more time.
Anyone else only have this class on Wednesdays and had to get up for the first time in a couple weeks?
Yeah.
This is the only class that I actually have to get up for at a specific time at all.
I'm on the other side of the spectrum, and I have 8 solid hours of classes on Wednesdays. So yeah, it's
That
a lot of fun.
sucks.
That's tough.
You're the only one who got kicked out. Zoom is not available anymore on the internet. So I'm glad we're in our meeting. Or maybe we're not. Somebody just disappeared. So some of you, somebody said they had 8 hours straight of class on Wednesday.
Yeah, that was me.
Were you going to have 8 hours straight of class on Wednesdays if you were at WPI this term?
Yeah.
So you did it on purpose. You can't complain.
No, I didn't do it on purpose. It's
Well,
just because
at
I
least
wanted to
you
take
knew
the
it-
3 classes that I'm doing right now.
All right. At least you knew
And
it
they
was
all
coming.
line up fine. Yeah.
You coming? If you're out here Zoom, we can, in just a minute, we can do our experiment we practiced, okay? You guys see Emily? Sure, no, because I'm sharing my screen. You can't see much. But in just a minute, Emily's going to help us do an experiment. But let's look at power forces and chip formation very quickly. Time is it? Okay. Still got time. All right. Energies, the ability to do work. This is just a quick recap from yesterday, because normally I have the slides up when we start. Power, work over time. We did all this already. Force times velocity. Okay. We talked about the machinery's handbook. Did anybody try to look at the machinery's handbook yet? Just to see if I was lying? Anybody? Nobody cares? Okay. Well, you'll have to use the machinery's handbook, and there's a video that shows you how to get access to it. If you don't remember, go to the Gordon Library website, search for machinery's handbook, and then follow the links. If you do it from the Gordon Library website, you may have to log in with your WPI credentials at some point, but it'll all work out. So C's our feed rate fudge factor. We got all this stuff. All right, good. And we talked about why we care. So let's just take a quick look. This is a quick video of some turning that we did. I think I've used this video before in class. Let's just take a quick look at what's happening. And very often when we do this kind of discussion, when we're talking about cutting, we use turning operations. And we use turning operations when we do this because it's got fewer axes of motion. It's cool. Emily's getting ready for the experiment. She's setting up props. So it's got fewer axes of motion. So there's fewer things to consider when we're doing it. So let's just see if I can close this little thing here. So let's just look at this diagram here for a second, right? So this is turning. And so what kind of turning is this if we had to characterize the turning?
OD turning.
So what we would call this, we call it, sorry, I probably shouldn't chew the ice cubes from the water. But once you start chewing the ice cube from the water, it's hard to stop. So what we're doing is we're reducing the diameter of the part. So we would call this OD turning, so outside diameter turning when we do this. And so we've got our we've got our original diameter, we've got our final diameter, we've got our depth of cut, which is half the difference between the two diameters, right? And so our feed rate is moving along the workpiece, and our speed, are you getting some ice there? They can all hear you. Probably shouldn't get next time if you decide to get ice when I'm doing a lecture, try not to get crushed ice, okay? All right, so I'll quickly go back just a little bit here and talk about what's happening in the turning. So we use turning because there's fewer axes. I guess I shouldn't manually try to control the video here. All right, so it zooms out a little bit. We can see what's going on. So this red part here is the chip. It's sliding along what we call the rake face of the tool. This dotted line here, back up just a little bit. Pause. Back up and pause. I think the internet's pretty slow right now. I probably shouldn't be using so much of it all at once. All right, let me get out of the video. Move on. Oh, the next one is also a video. I promise when we play this video, I won't try to mess around with the position. I'll just play the video. Do you guys still hear me? Are you still there?
Yeah.
Your voice is a little choppy,
You're kind of staticky though.
just a little.
Yeah, I think we've exhausted the capacity of charter cable here, and I'm gonna switch over to the phone for audio. Give me just a second. Is the audio better now? Is anybody still in the meeting?
Yes.
Yeah, it's
Okay, good. And I can hear you guys better, so I hope you can hear me better. All right, so when we went through this video right here, it's a close-up of what's happening as the tool moves through the workpiece. And at the end of the video, it rotates everything around. Oops, ended the video. All right, so did you guys all see the video? The tool was going through the workpiece. The chip was forming and sliding along the edge of the tool.
Yeah.
All right, good. All right, so I'm going to stop my screen share here. That may cut down on the the bandwidth utilization also. So this, start my screen share, and you guys should see me now, right?
Yes.
All right, I'll go with it. I assume you can see me. All right, and so as the workpiece is moving past the tool here, we've got the tool, we've got the workpiece moving like this. It's kind of interesting because we've got this, what we call the uncut chip thickness. And so that's just workpiece material is uncut chip thickness. Now, the chip also has a thickness here, right? And I've on purpose drawn this diagram so that the chip thickness is much different from the uncut chip thickness. Why is the chip so much thicker than the uncut chip? Because it's got the same molecules in it.
Are they more spread apart?
We've done work on the workpiece material, so we've changed the workpiece material in order to form that chip. And all of that energy or all of that power is applied right in this zone right here that we call the shear zone. And we actually model that with a plane that lines right up with this line here. We call that the shear plane. And so in order to talk about it, one of the things that we do is we measure the angle here, this angle right here, we call it the shear angle. And we use this, that's the Greek symbol, that's phi, right? Capital phi or phi or something. Somebody, I'm not good with my Greek, which is really weird because I took Greek when I was in high school.
I think it can be both depending on like where it's located in the
Yeah. Anyway, that's the symbol we use for shear angle. And this is the shear angle. It's that angle here. And so if we change that shear angle by changing other cutting parameters, so we don't have direct control over that shear angle. It comes from the orientation of our tool and the workpiece relative to each other. But if we modify that shear angle, we can make it take more or less cutting force to turn uncut chip into chip. And so the longer this shear plane is, the more energy, the more force it's going to take to do that. So the shear angle is really important to us. Now, we mentioned yesterday, so there is a resultant force. So there's a force here that is the force the tool is exhibiting on the chip. And so there's an equal but opposite force here that the chip's exhibiting on the tool, because since we're modeling this, we're going to assume that we're in steady state. We're not going to look at the dynamic forces, the dynamic loadings that happen in this. If you want to look at that, people get PhDs on looking at that kind of stuff all the time. So if you want to look at that, think about the PhD program. Right now, we're just going to look at the static forces. So we've got this resultant force here. There's got to be a force that gets applied along that shear plane. And so we would call that the shear force. And so that shear force goes out here. And there's always a force normal to the shear force, and we call that the force normal to the shear force. And so our shear force plus the force normal to the shear force have to add together to equal P. Now, if we're interested in the force that it takes to make that chip, so the force that it takes to turn the material into chip, we're going to look at that shear force system. When we're interested in the power from the machine tool, what we're really interested in is this cutting force system. So we've got an FC here. Need a better marker. We've got our FC, so that's our cutting force. And we've got a thrust force. And so the thrust force is FT and FC. So our thrust force is holding the tool down on the workpiece. The cutting force is what's actually making the power that the spindle is using. So that's times the velocity. The velocity again is the surface speed, the speed at which we're moving through here. So we've got that. And when we're interested, because this chip slides along the rake face of the tool. As the chip slides along that rake face of the tool, it makes friction, right? And so it makes friction here at that tool chip interface. And that friction force adds together with the normal force. Oops, to equal P. So this is friction force. We use F for friction force and N for normal force. And so these are the three force systems that we care about. Now, how do we move from one force system to another force system? In this case, what do we have to know if we know the friction force and the normal force, but we really want to know about the cutting force and the thrust force, what would we have to do?
They're both equivalent to P, so you would use that fact to relate the two force systems.
So we use that fact. So we use the geometry of the cutting operation to relate those two. And so what do we know about the cutting operation? We know this angle, the shear angle. And how do we know the shear angle? Or when do we know the shear angle? Can we directly measure the shear angle easily in our lathe? If I go back to the screen share, so if I go back to the screen share, we can see what the shear angle is here in this picture, because we've got a high-speed camera with a microscope zoomed in on that tool chip interface, right? So if we've got about, I don't know, $20,000 worth of camera and microscope equipment, maybe it's closer to $100,000, we could actually measure that shear angle. If we don't have that, what would we like to have? Would we like to have a mathematical relationship between the shear angle and something that's easy to measure? So let's investigate a mathematical relationship between the shear angle and something that's easy to measure. And so here's another diagram of the cutting operation. Again, we've got a rake angle, and that's the angle. Turn off the screen share. Can you see the screen, or can you see me right now?
We can see you.
Yeah, I meant for you to be able to see the screen, but I'm just going to turn that off for a second. So now you can see me. So the rake angle, let me get my cutting tool over here. I have a cutting tool somewhere. So the rake angle, so here's our cutting tool. And so it's just, I've got a lathe insert in a tool block. Here's our cutting tool. Here's our workpiece. And so as the tool's going to make the outside diameter of the part here, it's going like this. And so that shear angle is whether we tip the tool like this or like this. So if I tip the tool like this, I've got a positive shear angle. If I tip the tool like that, I've got a negative shear angle. And so that's as it moves across. So that's that shear angle that we can see in this slide now that I click share. And now you can see the slides. So as you can see the slides there, that shear angle, if we change that, so we measure that from the vertical. The rake angle we measure from the vertical. The shear angle we measure here. And then there's a simple geometric transformation where you can show that the tangent of the shear angle equals this RT, and RT is the ratio of the uncut chip thickness to the chip thickness. So our tangent of that shear angle equals RT times cosine of alpha, alpha being the rake angle, over 1 minus RT sine of alpha. Now, one time in this class, I gave the students an assignment to get extra credit points on their final exam. I said, if you can write a proof that proves that this is true, I'll give you like 3 extra credit points or something like that. Before I gave the assignment, I made sure that I could prove it because it had been a long time since I was in geometry class making proofs. And so I spent a weekend with sheets and sheets and sheets of paper proving to myself that I could prove it before I assigned it to the class. And what I didn't realize was I had given the class too broad of a purview. And so based on the assumptions I let them make, there was more than one way to prove it. So when I graded the assignments, not only do I have to give full credit to all the proofs that match mine, I had to also examine all of the proofs that didn't match mine to see if they were correct. So that's the last time I will ever give a mathematical proof as a assignment in class. So if you were thinking you were going to prove that to me and get extra credit points, sorry. Let's see what I got here. I'm going to turn the screen share off. Stop share. All right. So we've got the rake angle. Now our rake angle, or sorry, our shear angle can be related to that rake angle. So that's pretty cool. The other thing that we're going to want to look at here is what is the uncut chip thickness? So what do you guys think the uncut chip thickness is mathematically, or what's the definition of it? How do you know what it is? All right, we're going to pick up tomorrow with uncut chip thickness because before the day is over today, I want to do my experiment. And so I'm going to see if I can change my screen share now. So I'm going to share the screen. And I'm going to share this camera view here. All right, so do all of you now see like an orange thing?
Yeah.
And a panda with 2 squirrels and some flowers?
Yeah.
Yeah.
All right, perfect. Emily, I need help. Oh, there you are. Okay, Emily, please prepare the samples. Because it's going to be a little bit hard for me because I can't see what's going on the screen. I have to sit on the other side of the table, but we're going to go with it. This is an experiment that I normally do using the document camera in class. So, all right, you going to prepare my samples? And so again, I got my cutting tool insert. This orange block here is our fixture, and Emily's going to place the workpiece material in the fixture. Now, this is an experiment that you could potentially do at home if you want to. You don't have to have these fancy 3D printed fixtures, and you don't have to have a cutting tool. You could actually use a butter knife to do this experiment. But I want to watch that chip form on the edge of the tool. And so when I move the tool up and down right here, I'm changing the uncut chip thickness.
I don't see.
When I move the, can you see the tool?
No.
Oh, we just see a picture.
We can see a paused video.
You see a paused video. Well, that's kind of lame. You're supposed to
your
see
camera. So if you go to start video, you can, if you stop screen sharing, go to start video. Right next to it is a little arrow, and you can change your camera.
Screen stop share. I should be able to share the view.
Yeah,
from
so
the
start
other
video.
camera.
Right next to it is
Yeah.
a little arrow, and click the camera you want to share.
Oh, you know what it was doing? Oh, it was showing the app named camera. There's a way that I can share my other camera here, but I can change the camera view. Okay, I'll do that instead. I practiced almost all of this. I want to go to the Logitech Bria. And now, and I'm going to stop sharing. I'm not sharing now, right? Now you see the camera view in live?
No,
You see my hand?
I don't see anything.
That's lame.
I don't see that either.
All right. This is pretty lame.
James, you can move out.
So start camera.
I'm
you
gonna
see that?
share. Yeah, it should work. It says, oh, it says the video was stopped. I don't know why the video was stopped. Stop share. Start video. Cannot start video, fail to start the video camera because this app hasn't opened. All right, I've almost got it figured out. Close this. Then. All right, now you see the view I described.
Yay!
All right, perfect. This so much for practicing. All right, and you see Emily?
Yes.
Yes.
Perfect. All right, so now when I move the tool up and down, I'm changing the uncut chip thickness. When I move the tool this way, this velocity that I'm moving the tool, that's actually the surface speed. That's the speed that the cutting tool is moving through the workpiece material. Now, normally we get that surface speed by rotating the workpiece. But since we're doing what right now, the cutting operation we're doing is really like a planing operation. It's the surface speed equals the feed rate. So the feed rate is going across here, the surface speed equals that. Normally the surface speed comes from the rotation of the tool, so don't forget that. All right, so we've got our workpiece, we've got our fixture. I know that this fixture may be a little bit not quite good enough to hold the workpiece, so I'm going to apply a little bit of extra fixturing force with my finger, and then we're going to slowly take a chip across the top of the workpiece here. And you can see the chip form on the edge of the workpiece and flow up the rake face. Emily, could you take care of that chip for me? Okay. Now, I'll do it again. You will slowly make a chip across the top of the workpiece. And so at that time I had a little bit more down pressure. My uncut chip thickness was changing over time there, I think. We'll try one more time here. You make the chip across the top of the workpiece. Once more. Be careful, the cutting tool's sharp. Now, you guys can do this experiment at home too, and you might have a little fun doing it. You can try some different parameters. Emily, give me a butter knife. And so if you haven't figured it out yet, the workpiece is actually butter. Now this is kind of nice butter. This is grass fed. It's actually very delicious butter. But we could, and so if we change the angle of the knife here, we're changing the rake angle as we come across here. So I've got a rake angle of 0 right now. If I wanted to have a slightly positive rake angle, I can put the knife like this. And I'm using the back of the butter knife because the edge is flat. And you could use a steak knife, and then you change. So if you use the steak knife, you'd change the W factor, right? And so I've got a positive rake angle here. I've got my chip forming and sliding on the rake face of the tool. So we can do that with a negative rake angle. And if you alternate between that positive rake angle and negative rake angle, you'll notice that it takes different amounts of cutting force, both to hold the tool down, so that's our thrust force, and the cutting force, the force of pulling it this way. Let's see what else. You may want to have toast or a bagel handy if you don't like to just eat butter. But hey, butter makes everything better. And in this time of amazing weirdness, I do think that we need to have our comfort foods whenever we can. And so with that, I will leave you until tomorrow. Tomorrow again, we'll pick up at uncut chip thickness, and then we'll quickly get into force transformations, and then move on to fixturing, cutting forces, and Oh, say hi to the little. So this is a white squirrel.
It's the Panda Face.
You've met Sir Panda Face before.
This is Snowflake. I got him before 6 months. And this is Snowflake's older brother. His name is Avalanche.
Avalanche. So Snowflake, Avalanche, and Sir Panda Face. And with that, we'll see you guys tomorrow.
Bye.
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 Thank you.
Thank you guys.